Dr. P here. Today we're going to continue our conversation about circular motion. The example that I have for you is a car that's going around a curved track that is flat. So just think about you going in your car and taking a left-hand turn. The example that I have, this car is going to go forward or up and around in the counterclockwise direction at some speed. We'll call that VT for the tangential velocity. Now, of course, we know by now that anything that's moving in a circle is accelerating because the direction is changing, and that acceleration points in to the center of the circle. Doesn't matter where you're at, that acceleration always is going to point in, which we would call the positive radial direction. So because that acceleration points in, we need the net force that also points in. It's kind of hard to tell what forces are acting on our car from a top-down view. So I've drawn a picture of it from behind. When we look at this car from behind, where the radial direction is over here, we could label this R. We have the force of gravity that goes down and the normal force that goes up. That force that points into the circle, that's going to be the force of friction. Now, I know you're wondering to yourself, is this static friction? Is it kinetic friction? Well, if you think about the tires on your road while you're rolling forward, if you're thinking sideways, you don't want your car to go sideways. You want your car to stay on the road, and so we have static friction. We can remember that that force of static friction is less than or equal to mu sub s times the normal force. So the way that we solve problems hasn't changed. First we draw a picture, then we draw a free body diagram. In this case, we also want to set up our coordinate system where one of those directions is the positive radial direction into the circle, and then the other coordinate will be perpendicular to that. We'll call that y. The next step is always to sum the forces. Now, if you know and you've looked at step 6, it says stuck, sum the forces in the other direction. I'm going to go ahead and sum my forces in the y direction just because it makes sense. I know that the car is not accelerating up or down, and so the normal force is going to be equal to the force of gravity, which is mg. Okay, so if I were to sum my forces in the radial direction, that gives me my centripetal force. The sum of the forces in the radial direction is mass times the centripetal acceleration. That's Newton's second law. And then the only force that acts into or out of the circle is going to be that force of friction. The linking equation that we have for centripetal acceleration to velocity is Vt squared over r is our acceleration. Okay, so I'm going to use this equation down here for my force of friction, and I'm just going to put that right here to the side. Sometimes I have trouble with inequalities figuring out which way they should go, and this is a little bit, I think, helpful. So the force of static friction is less than or equal to mu sub k times, or mu sub s times the normal force, or mu sub s mg, which means the mass times the centripetal acceleration will be less than or equal to mu sub s times the normal force. We can cancel our masses, and that gives us that the coefficient of static friction is going to be greater than or equal to Vt squared over r times the gravitational field strength. Now, another way that we could ask this question is, what is the speed that we could go given some coefficient of friction? Just solve this for the tangential velocity then, and you see that the tangential velocity could be less than or equal to the square root of mu sub s times r times g. This means if I have some large coefficient of friction, of course I can go slow around that corner. But given the coefficient of friction, given the radius of the corner, that tells me how fast I can go before I fly off.